Okay, good morning, everyone. This is the first IoT Tech Talk of the year. We're very happy to welcome two colleagues from the University of Southern California. We have Bhaskar Krishna Machari and Jerry Powers. They're going to speak to us about their work and experience of over a number of years and about some future plans as well. In general, they are here because they're interested to work with us and find connections between the work that Google is doing and what they're doing. We have already sent them some of our IoT technologies in the summer last year, and they have deployed that and started a number of interesting projects that we're going to hear about today. The talk mostly Bhaskar is going to give is on algorithms and architectures for the future of the Internet of Things. And again, he's going to draw on about a decade of research in that space, sensors, and how to share the data and how to connect the cyber-physical systems and go all the way from individual use cases to smart city use cases, etc. We have some time set up for a Q&A, so while I guess you can also jump in the moment, please think about questions you want to discuss with the colleagues later in the Q&A stage. And without further ado, I pass it over to you, Bhaskar.
Thank you, Max. It's a pleasure to be here. So actually, before I begin my talk, let me mention again that this is a talk that I'm giving that is in collaboration with a colleague of mine, Jerry Power, who's here with us. And when I give this presentation, about the first half or so, I'm going to focus on some of the research we've done over the years related to IoT. And then towards the end of it, I'm really going to hone in on a new project that we've started. It's a collaboration between the School of Engineering and the School of Business. And Jerry is sort of my collaborator in that project. And so that's the part of the talk where I think both of us will pitch in. So the question I probably get asked the most about IoT is, what is it? And what does it look like from an academic perspective? And here's a slide that is my take on all of the things that are part of IoT. I actually use this as my intro slide for a class I'm teaching this semester to undergrads on IoT. And sort of to the left is the IoT edge. These are your sensors, your actuators, mobile devices, wearables, potentially even human observers, edge computing, and sort of taking all of the information from and eventually even to the edge devices is the bigger internet and software that might be running over the internet cloud, middleware, and at the other end of it, cloud computing, on which you might be doing various types of data analytics, inference, signal processing, and of course, the actual end user applications, which may be running through mobile apps, through other ways of interfacing with the application for the end user, and secure data storage and so on. So in the past decade or so, my research group in the Viterbi School of Engineering has been really focused very much on the left end of this chart, really looking at various problems at the edge of the Internet of Things, and in particular, a lot of work on low-power wireless embedded sensor networks, and also some work on mobile sensing, a little bit of work on mobile computing, robotic wireless networks, and vehicular networks. And I'll mention all of those in brief, but kind of give an overview of that decade of research and kind of come to more recent work, which is starting to get to the center and right of that chart I just showed. So a lot of our research at USC has been really leveraging a testbed infrastructure that we put together now almost more than a decade ago. It's called the USC TutorNet testbed. It is one of the first ever low-power IoT testbeds in the world. There's 100+ devices that are wired for power programming and for data upload, but they're actually just running a low-power 802.15.4 based stack for radio communications. And so this is a testbed that's deployed on the 3rd and 4th floor of the Ronald Tudor Hall, hence the name for the testbed. And over that decade, a lot of the protocols and software and algorithms that we've been developing have really been implemented and evaluated on that real system. And so many of the things that I'll mention in today's talk were really evaluated on that test bed in a realistic environment, giving us an understanding of what are optimal designs for various protocols across the various layers. It has played a big role in our collaborations with industry, as well as even used to evaluate industry standard protocols when they were first being developed and proposed. If I could just show very briefly, here's a kind of YouTube video that is just a time-lapse video of link qualities on that test bed, just to give you an idea of the kinds of things one could do with it. Here are snapshots of link qualities on the test bed on 2 different channels on the 802.15.4 radios that we have. Channel 18 is smack in the middle of the Wi-Fi spectrum. So it sees a lot of interference, and you see a lot of those red links, which basically correspond to poor quality links with link qualities that are worse than about 50%. And on the right side, you have channel 26, which is above the 802.11 spectrum, and so sees virtually no interference from that spectrum. The only red links you might be observing are really long links, which are weak because of signal attenuation, but not because of interference. And so all of the nodes that are on that test bed are basically programmable all the way down to the link layer. We can't touch the physical layer that's baked into the radio, but everything above that is modifiable in software. So to kind of resume, a lot of our work has looked at these multi-hop low-power wireless networks, rather like the one I just showed in that video, and looking at protocols at different layers of the stack.
In this video, I will show you how to analyze NS2 trace file. So in order to analyze NS2 trace file, we need some script.
So one of the problems we encountered very early looking at low-power wireless sensor networks is that you might easily have, for certain applications, a very dense deployment where you have hundreds of nodes that are all wirelessly communicating to a base station, but that are all in the same range of the same access point. So if you look at today's CSMA protocols, they typically have parameters, back-off windows, number of stages, etc., that allow you to tune what is the number of nodes for which they will perform optimally or will perform with high throughput. And if you actually operate outside that normal range, and it turns out the default values are typically suited for about 30 devices, 30 to 50 devices. So when you actually have 50, 60, 100 devices in the room using CSMA trying to communicate to that access point, the throughput per node actually not only per node goes low, which you might expect because you'd expect at least 1/10 of the bandwidth to be available to each node, but even the total throughput starts to drop because of inefficiencies caused by large numbers of collisions. And so we developed one of the first scalable medium access protocols that essentially has each transmitter observe the quiet time between transmissions and the ratio of that time to the time between transmissions, and adapt its back-off parameters on the fly, and showed that by doing this, you could actually scale much more gracefully without having statically set parameters to hundreds of nodes in that environment in a very dense deployment. And it really, the figures here are showing you hundreds of nodes and the throughput with the enhancement that we proposed staying essentially flat. And this carries through for much larger ranges as well. And a benefit of optimizing the back-off parameters on the fly as opposed to statically, or basically optimizing them dynamically, is that you also improve the energy efficiency because you spend far less time in collisions, which can be a big source of energy starvation for these nodes. Research on network protocols for these types of low-power multi-hop networks included work on en route compression. So this is data streaming through from multiple sensors that as the data is streaming through, you're also compressing it. Not only are you compressing the data coming from within a single sensor, but also spatially removing sort of this redundancy across different sensors as the data is streaming through, implementing essentially a 2D wavelet transform that is part of the routing mechanism itself. There's a work that we called SenZip. Another piece of work that we did that has to do with routing or data collection over these types of low-power multi-hop networks was the back pressure collection protocol. And the paper that we wrote about it in IPSN was titled Routing Without Routes, because unlike traditional routing protocols, nodes don't maintain a routing table and look up that routing table to decide who the next hop is going to be. Rather, they figure out on the fly the gradient between their local queue and the queues of nearby nodes, and essentially push packets in directions where there's a large gradient. And the best analogy I give to explain how this type of collection protocol works and why that's different from routing is, imagine water in your kitchen sink. You turn on the tap. All of that water is leaving the sink through the drain. And it's not doing that because there are routing tables written there telling the water droplets where to go. They're simply following a gradient, which is 0 at the drain where all of the water is being pulled out. And so essentially, by following the gradient, you can essentially drain out data from a network. And this way of thinking about routing as opposed to static routing gives you the benefit that when there are dynamics in the network, for example, caused by external interference, you can respond to them very fluidly. So you're not kind of building routing tables and tearing down routing tables. You're looking at local changes, local disturbances, and responding to them. And you can show that the overall benefit in terms of responsiveness, throughput, reliability is much higher using this type of a dynamic back pressure mechanism. Other work has included taking this type of back pressure routing in the context of mobile nodes where there's intermittent connectivity and enhancing the delay performance by adaptively adding redundancy in the form of multiple copies when that's needed. Work at the transport layer on speeding up the process of figuring out how much bandwidth is available in the network. If you look at TCP, we have a very classic seesaw kind of pattern where the source is trying to figure out how much bandwidth is available to it by slowly increasing the rate. And eventually, when it sees congestion, it cuts it back very aggressively. And that entire process is just to try and figure out how much bandwidth is available. We showed that for low power sensor networks, you could actually determine exactly how much bandwidth is available very quickly, communicate that to the sources so they don't have to spend a lot of time doing this blind search. And you could use that to improve the efficiency. So this is a few examples of the types of things you can do at various parts of the protocol there. Yes?
What's the sort of smallest type of sensor you can put this on? Because you need some code, right, to actually execute.
So all of the work that we've done, so the question is basically what type of nodes would be able to support these protocols that I'm describing. All of the work we've done are with really very old generation T-mode skies. So these are from 2006 or so. Hundreds of kilobytes of memory, and all of the protocols are written on top of TinyOS as the operating system, so extremely resource-constrained devices. And in fact, that's often much of the challenge here is how do you do all this and still keep your code very efficient? Absolutely, yeah. More recently, there's been a move, particularly in the context of industrial IoT, away from best effort protocols. So I showed you, to begin with, this protocol study that involved trying to improve the performance of CSMA. But if you're trying to use embedded sensors and actuators in an industrial environment, often you want much tighter guarantees on latency, on reliability, and as good energy efficiency as you can get. And the consensus in the community over the years has come around to the fact that for networks, let's say, of the scale of about 100 nodes, multi-hop, low-power wireless mesh networks, you're better off time synchronizing all of the nodes. And typically, we're talking about on the order of milliseconds or sub-milliseconds is what you need in terms of synchronization. And if you can provide that type of time synchronization, then on top of that, also do channel hopping and combine this use of time slots and channel hopping, what is called TSCH, to schedule every link and every transmission in the network so everything is predictable as much as possible. And in these applications where you might have sensors and you know exactly when they're going to transmit, or even if you don't know when they're going to transmit, but you give them a specified time at which to schedule a time for at which they should transmit, you sort of get a lot of guarantees, which will be hard to get in a completely best effort type of an environment. So looking at this class of TSCH protocols, which have evolved over the years, there's a number of different standards that are relevant to this. Wireless HART, IEEE 802.15.4e, and more recently, the 6TiSCH standards out of IETF are all kind of in that same space. Our work has looked at developing scheduling algorithms, in particular one that I'll describe in a little bit more detail called MCC, applying reinforcement learning and multi-arm bandits to do the channel assignment dynamically, because the channels that are good to use might change from place to place and time to time in an industrial environment, and other efforts that are sort of geared towards providing these high performance but with scheduling. So this is a work that we called MCC for multi-channel collection. And it was the first work in this space of low power wireless sensor networks to show that you could get demonstrably and also mathematically close to the maximum possible throughput in a real system in a way that was fair to all of the nodes in the network that need to communicate. So you're not giving more rate to some nodes and less rate to others. You're scheduling each of them fairly depending on the application needs. We could actually identify what the maximum data rate for collection from such a network for fair data rate would be, and show that the protocol achieves that value both theoretically and in practice.
So just a quick question. So when you say the channels are essentially learning how to optimize where to do their load balancing of sorts, how much of that today is manual versus how much of that?
Oh, it's almost entirely manual right now. It's typically these are just statically allocated. In this work, we're doing just some graph coloring and just statically allocating those channels. In more newer work since then, we've actually taken it to that next level of dynamically changing it based on the current samples. And the challenge is that if you have 16 channels and you're operating on some of them currently, you have to set aside some of your time to exploring the channels to see if they're good or bad, and then exploiting the channels that you know are good. So that exploration-exploitation trade-off is what's sort of tricky in practice to balance out, and that's work in progress.
Maybe a machine learning application possible there, where it can
absolutely. In fact, we're using online learning tools like multi-arm bandits for the exploration-exploitation trade-off. We're also using, and those are sort of non-Bayesian online learning schemes. We're also looking at deep Q-learning mechanisms for identifying potentially patterns in the channel availability. So if the underlying channel interference is caused by some underlying pattern sources, you might be able to learn that and learn to avoid them. So those are things that we're investigating in this space. So we're able to show that the overall throughput with our scheme MCC is on the order of twice what the state-of-the-art best effort schemes were able to provide. And this is because of the carefully algorithmically scheduled time and frequency slots. We're also able to show that the number of frequencies you need at any given time, if you were to pick the same frequencies for the whole network, for networks of reasonable size, on the order of 60 nodes or so, it's quite reasonable, typically between 2 to 3 channels, which out of the 16 that you have are likely to be good channels. We've done a lot of work on indoor localization, and in particular developed a class of localization algorithms that we call sequence-based localization. And the idea is that if you look at the signal strength from a radio beacon, that the ability to infer distance directly from that signal strength is very poor because of multipath effects and noise. And so you can't directly measure the signal strength, the absolute value of the signal strength, and infer where you are with respect to a source. But what you can do is look at the signal strength from a number of different known location beacons and rank order this set of received signal strengths and infer your location based on the ranking of the signal strengths. And we show that this approach, which is completely geometric, doesn't require any previous mapping of the environment or the location, provides roughly the same accuracy as more sophisticated schemes that require hours and days of training and kind of fingerprinting the environment to be able to give you location. So to give you a very short, brief flavor of how this might work, the figure on the left kind of shows 4 beacons, and all of these lines are perpendicular bisectors between pairs of beacons. So each of those lines kind of divides the space into 2 regions, one that's closer to one beacon, and to the other side would be closer to the other beacon. And what you can show is that every face in this kind of tessellation that you end up with corresponds to a unique ranking of the beacons with respect to their distances. So like the bottom rightmost corner has that ranking 4, 3, 2, 1, telling you that beacon D is the closest, then C, then B, then A. And from that, you can kind of, so if you measured these sequences, you would infer what location you might be at. And now there may still be errors, and now it turns out that the number of possible feasible sequences grows polynomially with n to the 4th, but the number of all possible sequences is n factorial, so you get some robustness to errors in the sequence as the number of beacons increases. And we've shown, for example, using that same test bed that I mentioned before, that this is just a student walking down the hallways of that building. So if you also incorporate additional spatial constraints, like you can't walk through a wall, you can really get very good accuracy in terms of tracking individuals in a space. And in fact, last year, thanks to Max and others at Google, we got a gift of some Eddystone beacons. We're actually looking at deploying our algorithm using those beacons and just your mobile phone as well. And at USC, we have had a deployment of this in the cinema school, where cinema students put together sort of interactive displays or stories that follow an individual as they walk through a building. And so if you know where they are and you know kind of what parts of the story they've seen so far and where they are in the story and where they are physically in the space, you can kind of keep the narrative going along with that. So this class of algorithms has been used to support applications of that type. Another work that's related to this indoor location that we're working on currently is a robotic radio signal follower, which is basically just a robot, something on wheels with a directional antenna that's actually a rotating receiver. And all it does is tries to identify the direction, angle, and distance, and estimate the distance of the source of a radio signal that it's locked onto, and try to stay as close as possible to that source. And we run a linear quadratic Gaussian controller on the robot to kind of continue tracking this individual as they go around. And so it's not a camera-based system, and it's working surprisingly well, typically keeping 99.9% of the time within 5 meters of the individual being tracked, indoors as well as outdoors. And what's neat here is that this would allow potentially a robot that might be aiding, let's say, a firefighter to be able to stay close to the firefighter where the visibility is low, there's a lot of smoke, but the RF signals are still getting to go through walls and smoke and so on. We've done for many years a lot of work on mobile sensing. In fact, we wrote one of the first papers that was in Mobisys 2009 on how do you estimate what the user of a cell phone is doing as they're carrying that phone around. This was actually back in the day when it was sort of Nokia N95s that we worked with. More recently, along that line, we have a center at USC that's focused on applying IoT and wearable sensing to the problem of personalized learning. Can we detect for students in a classroom when they're engaged, when they're bored, when they're frustrated, and can a teacher do something about that for groups of students in the classroom, and perhaps speakers at events like this can adapt their presentation in real time. In collaboration with General Motors, we've had a lot of work on vehicular communications and sensing. Just to give you kind of a couple of snapshots, we've done some work looking at how to disseminate information updates to vehicles on the road. So increasingly, our cars are becoming computational platforms. You want to issue software updates and patches to your vehicles on the road. And the state of the art would be to use the cellular system, and you have to pay per byte per car today. It's simply not financially viable for cellular providers to offer you a plan that's per byte and not per car, because they could get customers who would pay per byte per device. And so can you leverage V2V communication capabilities that are emerging in the form of DSRC radios, also known as wave radios, that allow cars within some range dozens of meters to be able to communicate directly pairwise. And so the idea would be, at the beginning, you seed your content in a subset of the cars on the road, and then for a portion of time, you're communicating in this V2V manner, and the information is disseminated in that form. And if you have a deadline, as you get close enough to the deadline, and you know there's a set of cars that didn't receive the content, those cars then will additionally download the content directly. So you're saving on the cost, you're leveraging the use of the V2V, but you're also acknowledging the fact that the V2V communication is not a deterministic channel because of the context being unpredictable and the propagation being potentially uncertain. I have a short video I might show. I think I have a little bit of time here. So this was another study with vehicular networks that is looking at how to store content in a vehicular repository. So if I have, let's say, I don't know, buses that are storing some content, and I want my cars to be able to download that content, am I better off simply making copies of the same files over and over again in multiple buses, or should I kind of code them more intelligently? And we showed that by using erasure codes, you can code it more intelligently in such a way that you break down your data into smaller chunks and then code them into, let's say you have k chunks, and you code them into n pieces in such a way that so long as you get k of those n pieces, you have the whole file. You're able to recover the whole file. And what we're able to show is that there's a huge benefit by using this type of coding, erasure coding, for vehicular dissemination. These are actually played back traces of cars in Beijing, taxis in Beijing. And what we were able to show was that as time went on, the number of cars that were able to get the content, so in this case, red is good, red means you got the full file, was much larger with coding than without coding, and was able to sort of, in some cases, even double the number of cars that would get it within a reasonable time. Other work in the vehicular domain. So when we talk about IoT, we think about typically sensors, actuators embedded in a static environment. There's some problems where having those sensors on vehicles would be a huge win. And one problem in particular is that of air quality monitoring. So today in big cities throughout the country, there are local agencies, for example, AQMD in Los Angeles, that has deployed a very small number, about 10 to 15 air quality stations that are measuring at very high quality what the various particulate matter and gases are, but it's only at 13 to 15 different locations in the entire city of Los Angeles. So the idea is if we could have vehicle-mounted sensors, maybe on the city buses, because they tend to drive around and cover a larger spatial area, that we'd have a much better picture of what's happening in our cities with respect to air quality. And we've done pilot studies, for example, with USC shuttle buses, where in real time we're able to track the measurements of various volatile compounds. We've done studies that look at if you have very large number of vehicles that have these sensors and the upload bandwidths are restricted, how do you choose which vehicles to pull that data from? And essentially becomes a problem of compression, but a sort of sequential query mechanism where you can choose one by one which cars to pull the data from or vehicles to pull the sensor data from, and stop when you're sort of out of bandwidth, but you've chosen those vehicles in such a way that you maximize the value for the data upload that was incurred. Very briefly, we're also working on robotic wireless networks with the increasing popularity of drones and robots in various applications. We think there's a real opportunity to use robotic nodes to improve the connectivity for wireless networks, especially for disaster rescue, remote operation type of environments where you may simply not have enough nodes to guarantee connectivity at all times. Can you basically leverage these mobile routers to improve and adapt the network over time? And just another brief illustration of the idea. Here's a mesh network with robotic routers in it, and there are two flows, a green flow and a red flow, where there's end-to-end communication happening. and the robots are moving themselves in place to help support those two flows currently. But over time, there are going to be traffic dynamics. The flows might change, new flows might kick in. For example, here we have a blue flow that's just joined the network. And so some of the robots that were allocated to the current flows are basically detached from those flows and move in such a way as to serve the new flow. And all along, the idea is there's a two-layer mechanism where the lower layer ensures that all of the movements of the robots do not violate connectivity of the network, and a higher layer that uses the fact that the network is connected to run a global optimization to identify what the currently active flows are, what their needs are, which robot should go where, and then tells the lower layer to make that happen. And so you're sort of constantly switching between a global view of the network and a local motion control.
So that's very cool. But I guess it doesn't necessarily, how does it work in a highly dynamic environment?
Right, so if the flows, the endpoints themselves were moving, then that's definitely the biggest challenge. So our
using the connectivity from the drones
are themselves moving, exactly, the endpoints in this case, yeah.
It's constantly shifting.
Yeah, so basically we're leveraging a lot of work that's been done in the control community on swarm robotics, and they have developed algorithms that try to maintain connectivity so long as it's feasible. So if my two endpoints were physically moving in opposite directions, at some point the network will partition. No algorithm in the world will guarantee that they will stay connected, right? But so long as they stay in such a way that there's some network configuration that exists which keeps them connected, the algorithms that people have developed in the controls community try to ensure that within that, so long as you're within the feasible region, they will move in such a way as to retain connectivity. So the endpoints moving will cause the robots to also move in such a way as to maintain the connectivity. So by way of just one sentence of detail, a lot of this work actually uses really cool math that boils down to algebraic graph theory. And the second eigenvalue of the Laplacian relates to connectivity. And they basically move in directions that maximize the second eigenvalue to try and maintain that connectivity. So they are flexible in that sense. If you get to the extreme where it's so sparse that there isn't actually a way to position your robotic routers to give an end-to-end path, then your robotic routers have to become message ferries. In other words, they may have to capture data from one place and physically move over to hand over data. We have other papers that are looking at this message ferrying type of a scenario. But definitely much more challenging. Because then you may also run into questions of not knowing where the nodes are when you're out of contact with them and so on. What I gave so far was really a high-level overview of many of the kinds of things we've been working on over really the past decade. Coming back to things that are currently active in our group at the moment, we're looking at several topics. Certainly, software-defined networks have really taken off for enterprise wireless and wired networks. We're thinking about what can they bring to IoT deployments, in particular for relatively small-scale deployments, having a centralized view of what's happening at every layer of the IoT protocol stack, all the way down from the physical layer, what power levels are being used, what channels are being used, what's the status of those channels, to routing decisions, to what's happening at the application layer with respect to what connections are currently active, which protocols are in use, who's talking to whom. Can you use, first of all, can you build such a centralized management system? And what would be the trade-offs in terms of the overhead that's required to collect that volume of information? And then you have some trade-offs. Do you collect it? What frequency should you collect it at? How fresh and useful is that information? But let's say we're able to pull together that type of a centralized overview of what's happening in the nodes of the network. That allows for interesting control and learning algorithms to be implemented now on the IoT system, because I know what is happening. I know what the sequence of events were. I might be able to infer certain causal patterns. I may be able to learn certain ways of operating and setting my parameters in the network that lead to more efficient performance, that lead to more secure and robust performance of the network. So that's sort of a whole area of research we're very interested in, which is for moderately sized networks, how much visibility can we gain? How do we bring online learning and control tools to improve the efficiency of these networks? So they're not designed and operated in open loop, but really in a closed loop. And that's something that in that community is still relatively new. We have really an incipient project that's trying to understand what can we do for computation. So when we talk about security in networks in general, really today the gold standard is transport layer security. So you're able to secure data as it's going end to end across the network. But in the context of IoT, a lot of times it's that the endpoint is not under your control. You're sending your data to some middleware, some cloud provider to do your computation, and maybe the data is so sensitive you don't want them to even look at the data while they're doing the computation for you. And so what choices do you have? The state of the art in the literature is a new class of encryption algorithms called homomorphic encryption algorithms that essentially do computations over encrypted data. And today, the state of the art is really prohibitively expensive for standard applications. Computations over encrypted data is typically about 100,000 times slower than computations over unencrypted data. And our hypothesis is that for IoT applications where your data is only arriving once a second, once every few seconds, maybe that's acceptable. A computation that might have taken a microsecond, if it's now going to take me a second to compute, that's 1,000,000 times worse, but still acceptable for my application, might be OK. And so is it that there are some limited applications in IoT where we could allow computations over encrypted data and build systems that are secure not only end-to-end over the communication channels, but also when they're being computed? We also have some work on edge computing, which I will skip the details of. I mentioned the TutorNet testbed, which has served us very well for many years. That really was a testbed for working on low-power wireless. We're trying to take that same methodological approach of being able to have a testbed to evaluate our ideas at some scale in a real system. And we're deploying a testbed across the USC campus that would have dozens of gateway nodes, hundreds of sensors, actuators, location beacons that can count and measure real things in the environment, people, cars, air quality, noise levels, spectrum usage. And it would be a testbed that we could use to evaluate software applications, but also at the lower end of it, devices and various platforms. And so this is very much in development over this year, and we're kind of excited about having another testbed that hopefully will last us another 10 years of interesting research. So let me kind of come to the second part of the talk, which is really a project that we're very excited about and that I mentioned is a collaboration with our School of Business and Jerry Power from CPM. So if when I present even to my students, this is what IoT is, the question that's even at the back of my mind is this picture, well, who owns all the parts of that picture? Okay. And today, the state of the art is that it's typically the same entity. In other words, if I am deploying an IoT application, I will deploy the sensor, I will deploy the actuators, I will write the code that runs at the edge, I will have access to a middleware where I will write whatever pub sub I need to write. I will maybe secure cloud computing resources from somewhere else, but I will manage the cloud computing resources myself. I will deploy my own analytics, and I will write my end user app, right? All of this is vertically integrated, monolithic, and there are problems with this approach. One problem is you might think of, let's say, a building in which you have sensors that detect whether there are people in the room. Now, that sensor could be useful for safety and security. It could be useful for energy efficient operation of the building. There may be other uses for which that sensor could be used. But if I have the sort of monolithic view of what an IoT system is, both of those applications will end up having to deploy their own proprietary systems, and they may or may not talk to each other, right? If I'm lucky, they're both from the same vendor, the same provider, they do talk, but maybe I'm not, right? Also, I may have existing systems that are simply not interoperable from the get-go. And if I am a device owner, I've deployed the sensor for a particular application, I make some use of it for my application that may or may not be enough of an incentive for me to even deploy my application. So it may be that my application will get me some revenue, but these devices that I need to deploy to make my application work really well are so expensive that I sort of think twice and I don't deploy all of the sensors I need even for my own application. And so somehow, what is the incentive for me to be deploying them at sufficient granularity? From an application developer's point of view, how do you access these devices that might already be in place in an environment that'd be really useful for your application, So you wouldn't have to go and deploy it yourself. Since it's already there, could you just make use of it? And then how would you scale such a system? Let's say you figured it out for one building. How do you do it for another building? How do you do it for two cities when you know how to do it for one city, and so on? So all of these questions are still, I think, open challenges. And really, after some thinking about, at the core of it, what seems to be the issue, we felt that it wasn't a purely technological question. It wasn't a question of creating a standard that everybody will agree to, and therefore everybody will do the right thing, and therefore everything will be interoperable, right? There's plenty of standards out there. In fact, the problem is the first time somebody says we need a standard, everybody says, here's another standard. We all agree we should have as many standards as possible, and that brings you right back to where you were. I think the fundamental problem is really an economic one. It's from the get-go, do you create a system that allows the device owners, whether they're sensor data providers or actuator owners, to realize value for what they're deploying? So that gives them an incentive to deploy. It gives them an incentive to share what they deploy with other applications that may not have been the original intended application. It provides potentially an incentive for application developers to consider applications or enriching their applications in ways they wouldn't have. It provides completely new types of markets. It might allow for a data broker who says, look, I don't have sensors, I don't have an application, but I have these algorithms that can clean raw sensor data and make sense out of them, can fuse data from multiple sensors, can visualize them in interesting ways, and I can provide this service to any application developer that's interested, and I can do this on these types of sensor data, except I'm not a device owner, right? So a marketplace that can bring together these types of device owners, data producers, data consumers, data brokers, we think might be conceptually different from yet another standard for IoT systems to talk to each other. And that's what we call i3, an IoT marketplace platform. i3 stands for Intelligent IoT Integrator. But quite frankly, I just like the acronym, so we've kind of forgotten what the original expansion was. Here's just a different view of what the i3 platform is really doing. Is it's bringing together these different types of individuals, marketplace operators who are maybe hosting that i3 platform in some context. So the context might be a building, a campus, it might be an enterprise, it might be even a small town, a city. It brings to connect to that platform device and data owners, sensor owners, actuator owners. So in the context of a city, for example, you can imagine the Department of Transportation has deployed road traffic sensors. The Air Quality Management District has deployed air quality sensors. You have some commercial company that's deployed some other kind of sensors that are measuring, I don't know, energy. And so all of these sensors are deployed in the same spatial area. They all plug into the same local sort of administrative controller. And then your IoT applications that are interested in operating in that region are able to come to agreements, whether they are monetary agreements, whether they are other agreements. So for example, maybe the DOT is perfectly fine sharing their data with other government agencies, and they don't need to be paid for that. On the other hand, there may be other opportunities for a company that's deployed devices to be able to monetize their sensors and actuators. And so the marketplace essentially provides this matching function, this ability to enter into agreements, monetary or otherwise, about data ownership, data use, maybe even data privacy. And the marketplace also allows for third-party data brokers to show up to the platform and say, hey, I see there's these types of sensor data available on the platform. I will buy that raw sensor data, process it, and resell it in this refined way that is now also on offer on the marketplace for people to buy. And all of this is not archival data. It's not stored data. It's real-time, both sensor data and actuation access that is being managed by the platform. So there's a couple of analogies I'd like to draw to the traditional internet in this way of thinking about scalability and interoperability. So with respect to interoperability, a lot of people credit the narrow waist of the IP standards as being really influential in making everything work, right? So applications run on IP, IP runs on everything. So our analogy here with i3 is that it provides that type of a narrow waist for bridging the gap between end user applications and devices. Where today you have silos of individuals deploying devices and building applications around them, we believe that a platform like i3 could provide that narrow waist, allowing a rich diversity of applications to be able to communicate with a rich set of sensors and actuators below.
So I very much buy the idea in terms of facilitating app development and reuse of data for lots of purposes. But obviously, getting the privacy implications are enormous. And I'm wondering, who do you imagine is going to be managing this IoT layer?
Right.
There are legal ramifications if you don't get data access correct.
So let me defer that question to our Q&A session right after this, because that's absolutely probably number one in our list of things to focus on is the privacy implications of such an architecture. Yeah. And certainly this is, at the outset, let me reinforce that this is work in progress. This is work where we're coming out here and saying, these are ideas, what are questions we need to be digging deeper into. So this is certainly a very valid and excellent point to bring up. So the other analogy I want to make to the traditional internet as to why it's scalable. So we talked about why it's interoperable is this notion of a narrow waist. Why it's scalable is that you don't think of the internet as one giant network. In the same way, you don't want to think of the IoT as one giant IoT system, right? Traditionally, we've had this notion of autonomous systems. And roughly speaking, each autonomous system is an organization. And roughly speaking, most autonomous systems have some spatial proximity. So many cases, the autonomous system is an enterprise, is at least somehow geographically described, not always, but it's a reasonable first approximation to what an autonomous system does. And so our view of what i3 should look like is not a single monolithic platform that every device on the planet would connect to and every application in the world would connect to, but really as a series of autonomous systems that we refer to as an i3 domain controller. So the picture of that marketplace is there's really one for each domain. And within that domain, it may make sense because within a city, within a campus, or whatever that granularity is, you're deploying applications that are somehow local to that zone. And so the majority of applications, the majority of devices, the data flow stays within. But there may be interactions that cut across these domain boundaries, just like we do on the internet. We have inter-domain routing when we need to move from one autonomous system to the other. And so you may have applications that get, let's say, the bulk of their data from a local sensor, but need some data from a sensor that's remotely deployed. And so can we build an architecture that has peering relationships between i3 domain controllers? So you have, maybe there's a San Francisco one, maybe there's an Oakland one, and there are ways in which relationships have to be worked out, allowing for the movement of data, and then worrying about all of these other issues of data ownership, privacy, monetization, and so on. So again, architecturally, we think the way to think of scalability is think about autonomous localized systems and then interconnecting them the way the internet was scaled up. And so what a possible single domain controller might look like, this is really some of the boxes we've started to fill out. There will be interfaces for buyers and sellers and brokers. These interfaces allow, for example, sellers to specify what types of data they have available, what conditions are required to be fulfilled before that data can be accessed. For example, they may need some legal certification to be provided before they will allow that access. And whether that should be managed ultimately by the administrator of i3 or by the original seller itself, that's, those are design decisions one would have to make. What pricing you're offering for your various sensors and access to actuators. Likewise, for the buyers, an interface that allows them to identify what's available, and perhaps there's a recommendation engine at the back that gives them, given this is what you're looking for, here are some data streams that might be useful. Allows them to enter into agreements, make purchases, and once they've done that, have the system essentially recognize that they're now, and that once they've met whatever requirements the seller might have or might be legally required, that from that point on, they have the necessary credentials to be able to access the data. So to the sort of right side of this figure is the authorization component, where once the appropriate agreements and payments have been made, the buyer and seller are able to connect through a pub/sub API, and it's basically allowing them to unlock the data flow once those agreements are in place. And we're initially thinking of going with something that's become quite standard in IoT for real-time applications, which is to use different forms of publish, subscribe, middleware. MQTT initially is what we're working with, but there's plenty of options out there, commercial as well. So there's also one of the functions would be to meter the data, just as you meter the use of energy or utility or data for wireless provision. Here, you might meter the provision of data to a buyer of that data, and that metering might lead to, what the bill might be for that month for what you consumed in terms of data and so on. Really, this is just a sketch. We have some very simple proof of concept demos that we've put together, but the core questions of what are the types of agreements that might need to be in place. So to give you an example, maybe your sensors collect personally identifiable information that you want to use for research purposes, and the agreement says that you can do that so long as you've filled out or you've done an IRB process and it's been approved, right? So who checks that that's happened? Is there some direct mechanism for it, or is it just something that's left for the seller to verify independently? I think those are some questions that we're looking at. Questions of data formatting. So should the i3 platform also provide a set of standard formats for all of the different types of data that are out there to facilitate further the ability for application developers to create their applications? Or do you simply leave it to the seller to specify, this is the data I'm providing, here's the format, and then the application developer's job is to figure out how to write whatever code they need to make sense of the data that they're getting. Ultimately, we think these types of open platforms might have to coexist with closed platforms, and how they will do that, and with applications that use, for example, proprietary building controllers. Do you need to write software that's like a shim layer that captures whatever you have available centrally from a proprietary interface and then throws it into something like the i3 platform? Do you have the ability for closed applications that are using proprietary data to also access the open platform? Absolutely. Do you allow, basically, what are the different combinations of open and closed approaches to application development and legacy versus new platforms that might need to be available? We think you have to be as flexible as possible at the early stages to really grow a system like that. So our ongoing efforts are really building, and I'll be the first to admit, an academic prototype of i3. I'm the first to recognize that my PhD students' code often is just good enough for us to be able to write a paper, and I wouldn't put any real applications at risk by having that be the main system out there. So one reason we're really interested in connecting with industry is to bring on board folks from industry, as well as from governments, actually, looking at these types of smart city platforms to really engage with us and put together a consortium and really make this go beyond an academic research effort. We are hoping that as the software for i3 is being developed, we're able to prototype and demonstrate it on the USC testbed that I described that's being developed. We're talking with on-campus users, our facilities management services, our security folks. USC with about 40,000 students and faculty is really almost a miniature town, and we have our own agencies, like I said, providing everything from security to energy to various aspects of operations. And so we want to kind of start with demonstrating that this really works at that scale, and then also trying to connect with local civic governments to try and build out further. So I think I'll stop there. My colleague Jerry and I will be happy to take some questions about the i3 work and answer them.
So the i3 marketplace idea is a pretty cool concept, and I know it's in early development phases. I guess what thought do you think would be in place or could be in place to protect i3 from the very incentives that caused it to exist? So say another university comes up with the i4 marketplace and has their own protocol stack, and they're trying to become the clearinghouse. How do you build the right incentive structure to respond to that?
One versus the other.
So what we're planning to do is roll this out.
Jerry, could you go?
Oh yeah, maybe we should.
Yeah.
This one should be okay.
So the idea is to roll this out as open source systems. So with different people contributing. So if another university comes along and says, hey, we've got this other idea, they could actually take it and contribute it to the process. Then basically I3 becomes really more of a distribution mechanism. We're thinking about this when we were thinking through this process. We were thinking about the early days of how the internet itself evolved, where lots of different universities and lots of different companies were contributing things. Certainly Bhaskar talked about how do you take corporate, I mean, some corporations that have had drivers and know how to interface with their legacy equipments, they could write drivers, put it in. It becomes then distributed to lots of different cities, lots of different universities, and becomes kind of a way of sort of seeding and encouraging growth of the market.
I think part of the answer is that it's meant to be an open effort at this stage, right? There's no, at least from our perspective, there's no, you're not selling i3, you're kind of building it out, and it's in everybody's interest to sort of get in on the ground floor and help build it out. And so hopefully the i4 people will come make i3, i4, and that, that would be a good thing overall.
Have you thought about how addressing would work on i3? Like as a buyer, how would I specify what sensors I want to talk to and what kind of data I want?
Right. So I think our version 0.1 of this is essentially the buyer first has to physically see somewhere what's available, and there has to be a description of what's available. And so the seller has to post on the marketplace, these are the types of data I have, this is what's available, these are the rates. Okay. And so what and of course you can flexibly change what format you can express that in, and maybe try to automate it to some extent. But ultimately, there's this two-step process where first the seller identifies what's available to buy, and then the buyer looks through that and selects and learns for each of them what is the price, what is the, maybe there's some legal issues around acquiring or using that data, or agreements that have to be set in place before you can do that. So, so it's sort of this negotiation process that has to take place. Once that, and then the buyer has to agree to those terms, pay for it. Once that agreement is completed, then the buyer gets access to the keys to be able to receive that data.
And that's the basis of starting, but as you think about IoT market growing and expanding, basically it makes room for then like IoT recommendation engines that says, all right, you're looking for this kind of data, here's the stuff I would recommend, and the other way around too. So it really becomes sort of an ongoing process.
So I know a lot of folks will have to drop off to other meetings, so I wanted to get 2 points out. A, I think we should quickly hear your thoughts about the privacy and data ownership and ideas that you had there. And possibly even more importantly, everybody who is here or who you think is interested in learning more about this and considering how Google might play a role, please get in touch with me or just follow up on our IoT discuss list to see how and if aspects of this might be relevant for our work here.
So go ahead.
We can talk about privacy over lunch too, but maybe we should ask if there's anyone on the bridge.
Anyone from on Hangouts interested in asking a question? I know we had folks from our threat team who are obviously very interested in the 15.4 space that you mentioned earlier on. Did you ever consider or weigh the use of thread against the usages that you actually
yeah. So thread has been something of keen interest to us, and until I want to say about a year ago, we couldn't really access it and deploy it. I do have a student who's starting to look at thread as an operating system for some of that.
Follow up on that too.
Yeah, I'd be very interested to connect with them.
So real quick on the privacy, while we still have people online, we've actually been thinking about it as sort of a trust, a rating system. We're basically in a three-way rating system effectively, where basically the users would rate the application providers, the people who are buying the data, and sort of saying, here's how well we trust them, and sort of become sort of a community-driven process. Also, the application users then are basically rating the users for the veracity of their data to make sure is that data really hasn't been integrated, tested, so that there's full visibility and transparency on that. Then between different i3 administrators, they actually have to negotiate, negotiate a process as to whether they trust each other to sort of exchange and participate with each other. ultimately, our thinking started out thinking that these people, because trust is like a critical issue about privacy, because it's not just is the data private, but actually do I trust the person to actually maintain itself. So we're thinking that the initial systems, for instance, at USC might be rolled out over the campus, where basically they are trusting the campus administration who runs the security for us. So I'm going to release my data because now I know security can see me. If there was a catastrophe, they could respond quicker, faster. I have a real reason for sort of trusting them. It rolls out then into cities, into other places, and we sort of start growing it like that. There's also the idea that we built into there is that these administrations could actually even be like the Heart Association. So for instance, if you're walking around carrying your cell phone, reporting your location information, that might go to the Heart Association. The Heart Association is then selling the data to users, and it becomes kind of a way of sort of giving back by basically just participating, but people tend to trust organizations like that.
Right. So trust and transparency are a huge part of the system, and a natural thing to incorporate. But I believe there's a lot more that can be done in terms of giving users some control.
Absolutely.
What happens to their data? So I'll give you a simple example. When you distribute data to other people, they don't always have to see it in its full-fledged
Right.
raw form.
Could you anonymize it, for
Summarize
instance?
and aggregate based on who you are, your role, and what you do.
Right.
Even the Heart Association maybe doesn't need to see everyone's. You don't need to know this measurement is
Yeah.
mine. You just need to know
Yes.
the average.
Absolutely.
The variance, right?
And if I could speak to that just briefly, so I mentioned that we're using publish, subscribe middleware. We have ongoing research doing something called publish, process, subscribe that does exactly that. In other words, you get published streams and then you create aggregated versions of those. And a user that's subscribing to an aggregated version of streams is able to get just the aggregated version and not the raw data.
Yes.
Great idea.
Yeah.
That's one way. That's one way to build in. Yeah.
I also am
Privacy.
very happy to see that you're thinking about secure multi-party computation, because I agree with you that things can be done when they're kind of focused.
Right. Exactly. So, and also maybe you don't need to try to compute every function. If we can focus on certain types of aggregations that are relevant to the applications, maybe that's more doable.
Okay, let me invite everybody in the room, and if you're on campus and want to come over to Big Table, we're going to move over to lunch conversations, so you can also get in touch. We might have the possibility to arrange a meeting with Bhaskar and Jerry later at Coffee Lab, and certainly to follow up. Thank you so much. That was really interesting work, and I hope we can build on it.
Cool.
Thank you, everybody.